Okay, so thank you for inviting me. And in this talk, I'm going to go big picture, uh, just looking at where computer vision is and what would be profitable for us to focus on as a field. And then in the later part of this talk, I will be very concrete and talk about a line of work and compositionality in tasks. But I think to get the mood, I have to start with some general remarks. So the general remarks I want to start with are the major progress we have had in object detection and instance segmentation. And I just picked a slide of output from Ask RCNN. And I think this is very impressive. I mean, we have had great success with this and some more results. And the question is, are we done? What more remains to be done? What should the field focus on? And that's what the purpose of this talk is. So I want to start with 4 criticisms of where we are today. And these are the limitations of supervision, static dataset AI, and perception disconnected from action, and the semantic gap. So let me get into each one. So the first one, a lot has been said about this, that we have succeeded, but we have succeeded because of lots of supervision. And we could continue to do this, and the big companies certainly have budgets which can support keeping on doing supervision. The problem is that there are always lots and lots of categories and examples in the long tail. And for these, we'll never have enough examples. So it's not a case of labeling. We'll just not have enough examples. So in that setting, it is going to be a few shot learning problem. Second point is that humans are not able to provide supervision for certain kinds of outputs, such as 3D shape. It's not easy for them. So I think it's not just for scientific and aesthetic reasons that we need to find alternatives to supervision, but very, very practical reasons. And since this is a topic that lots of people are talking about these days, and the rubric of self-supervision, I'm not going to say more on this right now. Second remark that I want to make is that we need to move from static data set AI to embodied AI. So we had a great success with data sets, and that was wonderful. And that's what really made the deep learning revolution possible. But this is not enough. This is what we see if we put a camera on our head. And this is a slide from Christian Grauman. And we need to have intelligence, which is an agent, intelligent agents, and they need to work in a world like this. So how are we going to get there? Okay, so that's point 2. Third point, this is perhaps the most important point in some sense, if you think about the context of perception in biology, is that we have been pursuing perception disconnected from action. So here's a slide which is like a big picture slide about how intelligence developed. So starting from like 550 million years ago, when the first animals which had some vision and some movement developed. And then there was this so-called Cambrian explosion. And the two go together, because what's the value of movement? The value of movement is that you can go to various places to get food. Well, but then you need to know where to go, which means that you need some perception of where is the food. And once you have that, then you're going to get predators who decide to eat other animals. So then those prey have to learn to camouflage. So therefore the predators' visual systems have to get better. And then they have to move faster, et cetera, et cetera. So it causes a arms race. And this line of Gibson, we see in order to move and we move in order to see, is really fundamental. And for the larger part of the evolutionary history of perception, in fact, this is the key loop, the loop between perception and movement. When we come to the last 5 million years ago, then we have the emergence of bipedalism. So we are able to walk on the ground and have our hands free, which can then be used for tool making and so forth. And there's the opposable thumb. And so that's when there's this flowering of humans as tool makers. And then, of course, language and abstract thinking comes in the last 50,000 years or 100,000 years or whatever. But my point is that we cannot think of perception in isolation by itself. We have to think of it first in the context of movement and then for guiding action like manipulation. But there's a lot of subtlety about this, and I will focus on this later in the talk. And finally, I want to remind you of the semantic gap. And I think Odd Oliver's talk actually addressed a lot of stuff related to this, even if she didn't use exactly this terminology. And here's my favorite example, which is that when we look at this image, we see a lot of stuff here. But what our computer programs see is relatively boring, right? They can detect people, put bounding boxes, maybe even convert them to 3D. Whereas when I look at this scene, I mean, to me, it has a certain richness. I mean, this guy is looking at this woman, the woman's playing music. There is, at her foot, there is this bag in which there are probably some dollar bills. So this guy is trying to decide, should I put in some money? Maybe I need to catch my train, etc., etc. So the relevant question is really, will this person put some money in this other person's tip bag? And that's not what our computer vision systems focus on. We focus on all, in some ways, the trivial stuff, right? And as we get to richer and richer applications, we need to get to this kind of interest and functionality, intent, etc., etc. Another point that I want to make, which is with respect to natural language. I mean, that's our sister field. I mean, the effect of deep learning has been most impressive in computer vision and natural language, and much less so in robotics. But in natural language, they have amazing systems now for translating from one language to another and so forth. But their systems do not really know what any of those words mean, right? So they can translate the word bank from English to French without knowing what people can do at banks. And this refers to the symbol grounding problem. And this is an old paper on this. And the point is that the symbols have to be connected to entities in the real world which have perceptual and motor affordances. And that's what we need to do. So we can not remain isolated from that. Okay, so here's a sketch of where we should go. And I've talked about this before, but for people who weren't in the audience at last talks, I'm going to summarize this very quickly. So my proposal is that we take Turing's proposal very seriously. Turing said this in his 1950 paper. He said that instead of trying to produce a program to simulate the adult mind, why not try to produce one which simulates the child's? If this were then subjected to an appropriate course of education, one would obtain the adult brain. So let's be inspired by child development. And there's the difference is that Turing wrote in 1950. This is 2020. So in the last 70 years, our psychologist colleagues who work in child development have uncovered a lot of knowledge about how children learn. So, for example, they explore, and one could in fact think of them as scientists trying to construct hypotheses of the world and trying to verify those. So my colleague Alison Gopnik has a book called The Scientist in the Crib, referring to children. So this child who's in the crib is playing, she is batting at objects, so therefore there's hand-eye coordination, there is sounds, there is smells, there is vision, there is experimentation, etc., etc. So this child, when this child goes to the zoo with her mom, at that point, the mother just gives one example of a zebra and that's enough. Whereas our computer program needs 1,000 examples. I want to recommend to people in this audience that in the embodied AI workshop, which was on yesterday, and I think it's also on today, there were two talks, one by Alison Gopnik and another one by Linda Smith. And both of them, the recordings are there. And these are senior researchers in child development, and they're both given talks, which I think would be an easy entry point for many of the people in the room to understand a little bit of what is going on. So I mentioned Alison's work on how exploration is key to childhood, but a point from Linda Smith, which I think is worth making, is that children are exposed to very few examples in the early stages of life. They don't see zillions of objects and they don't see zillions of instances of those objects. But there are a few objects that they see a lot of and they explore a lot of. So they squeeze a lot of value out of a relatively small number of examples, which is very far from what our computer programs do. But anyway, let me not steal their thunder. You should go listen to their talks. So, here's a slide which kind of summarizes some of what the child development people can tell us. I picked this paper, but you could pick many others. I mean, there's a huge literature, but I picked it mainly because it has some bullet points that I could use for my purpose. And it's embodied cognition, so agents which are acting and interacting in the world. And they have this short list, which I think is worth going through. One is multimodality. So you have, when a child is interacting with the world, he or she is acting. So there is the so-called efference copy. So the command that you issue to your arm, hand, etc. There is the signal from vision, there's a signal from sound, there's a signal from touch, and all of these are sort of working together. So in a sense, supervision is much less necessary because these modalities can cross-supervise each other. And there's now nice work going on in this space between vision and audition, but also between vision and touch. Incremental, this is essentially the idea that you build on top of your previous work. I think this is connected to the theme of this workshop on compositionality, and I'll talk more about that. Be physical, which is that you act in the world. Explore. Yes, so there's the explore-exploit trade-off that we have, and children do a lot of exploration. But they do this exploration in a much more generic way. It's not driven purely by doing a certain task. So reinforcement learning is a very, very narrow framing. And whereas children are driven by just exploration and they build models of the world which are much more general in nature. Be social, learn from others, language. This is where the weak supervision comes in. So a word on exploration. I think the challenge has always been, how do we do work in active perception? Because we can't just work with static data sets. So we need simulators of environments in the real world. And there's been a line of work in that. Gibson is one example. Habitat, this is out of Facebook. AI research, another example. AI to Thor, another example. These have their respective strengths and weaknesses. But my point is that at this point, one can do research in active perception because we have the tools. So this is advertising the stack in Gibson, and it has basically this philosophy that we only take environments which are captured from the real world, very, very high, very fast simulations. So that's a very important thing if you want to do learning. And then there's a variety of tasks on top. Social, okay, so we don't all start out as if we were 100,000 years ago hunter-gatherers. No, we all live in a culture. We have knowledge which is transmitted from one generation to the next. And that's something we can keep in mind. I think here's an example. So this is work where we are trying to have this humanoid learn how to do cartwheels. So we can start from videos, then we can recover the 3D structure. So this is now a computer vision technique we have become pretty good at, and then use that to trying to imitate that becomes like a signal, a dense reward signal for training a policy. And by having a policy, you keep it general. It's not just copying, but actually has versatility. There's a physics simulator built in there and so on. So I like the term imitation because that's part of how children interact with adults. It's not like just recording a certain experience and replaying it. So there are the earlier versions of imitation in robotics are extremely crude. I think that we need these much more sophisticated versions. Okay, and then language. I won't have much to say on that. I want to make one last philosophical point before I get into more nitty-gritty stuff, which is that AI systems need to build mental models. Again, this is something we have neglected. So we have been doing stuff which is specific tasks and just do what is necessary for that specific task, whereas even as far back as 1943, this is a quote from Kenneth Craig, who was a psychologist, and it's a brilliant statement. If the organism carries a small-scale model of external reality and of its own possible actions within its head, it's able to try out various alternatives, conclude which is best. So that's essentially what enables planning and reasoning. We don't have to act in the world, we can imagine the consequences of our actions. And this lesson was taken very seriously in the early days of cognitive science and control. So back in the 50s, that's what distinguished these fields, because they believed in these internal representations and models. The control theorists, they had this very mathematical abstraction: x dot equals ax plus bu and y equals cx plus du. Those abstractions enabled them to make a lot of progress. I mean, people like Kalman and so on. But it's really about having models of the dynamics. And I think we neglected a lot of this when we have in the last few years, particularly with all this emphasis on model-free reinforcement learning. I think that's a bad idea. I think we should go back to this old idea and so on. And I'll make this one remark, which is that what's called common sense, it's a very loaded term. It's been important in the last 60 years of AI, but what does it mean? Sometimes it means just collecting facts and typing them up in predicate calculus. That's part of common sense. I mean, so there are some facts like, Paris is the capital of France. Now that's in fact easy to deal with. We have techniques like knowledge graphs and so on for encoding that knowledge. What common sense really is a collection of models and schemas. What happens in particular situations? And I think this is quite related to what Aud said in her talk. So we have models of situations and how things are likely to evolve. If I'm at a restaurant, how are things likely to evolve? The person who came to me with a menu, perhaps he will come back later and ask me what food I want to order, etc., etc. So, anyway, so this is the large scale picture for what I think makes sense for our field, given where we are in 2020. We should take these lessons seriously. We've learned a lot from biology in the past. For example, the whole structure of ConvNets really comes from Hubel and Wiesel, 1960. And then someone like Fukushima created neural network models with exactly these layers of simple cells and then pooling and then simple cell and then next layer of filters, etc., etc. And what Jan LeCoultre et al. Added was that this could be trained using gradient descent and using backprop to compute the derivatives efficiently. But that's just one of the insights we can get from looking at the literature in biology and psychology. There's a lot more. And I think that the stages of child development provide a very good structure. And there are zillions of papers to be written building on these insights. So I've tried to summarize this as there is supervision, there is inbuilt stuff, there's supervision by observation, supervision by interaction, supervision by culture. And let me make one comment on this will be slightly controversial, but it's worth making, which is that, yes, we have all these techniques or some versions of these techniques in machine learning, right? There are all these names that you see in the slide before. But does that mean that, okay, we're done, that just do these things and that's it, that's child development? No, I don't think so. I think the typical story that I see is that we take some problem some idea, and then we create a mathematical model for it. And often it's quite simple-minded. And then we just focus on that. So think of continual learning or lifelong learning. I mean, in the context of human child development, it's a very rich thing. It's various stages of development. If you want to read a scientist, Piaget's constructivism comes to mind. What do we convert it to in machine learning? We've converted it to the problem of sort of avoiding catastrophic forgetting. So we have a neural network. We are going to train it with some examples. And now we no longer have those examples, and we add some new examples. And then what happens is, in due course of time, the neural network is unable to replicate the input-output relationships for the earlier examples. Okay, so that's the problem of catastrophic forgetting. It's been known for like 30 years. And so the whole game is, okay, how do we deal with catastrophic forgetting? But it's a very, very narrow definition of the problem. In fact, it may be that in biology, this is dealt with trivially because we actually have very good memory. So we may have episodic memories of lots of stuff. We may not train the lower layers of the network and just train the upper layers of the network. So we have created a whole field, and bunches of papers are being written on it, but it is with a very narrow formulation of the problem. Reinforcement learning, another example. It basically is a very narrow formulation of the problem of how do we get an agent to learn how to combine perception and action. Typically, the notion of perception is very, very limited. And so it feels very much like the kind of conditioned reflexes and behaviorism which were common in psychology in the era before cognitive psychology. And yes, we have dressed it up and so on, but that's what we are doing instead of the more sophisticated views involving models, etc. So I could go on, but I'll drop it there. What I want to do is to encourage people to go back to the source, look at the core ideas from child development, and find better models and focus on how to do our underlying AI problems better, rather than chase up on one particular formalism which somebody has made up, and it's not necessarily a good model of what actually goes on in child development. So with that background, I'll get to be more concrete now, and I'm going to talk about compositionality in tasks, and I'll leave enough time for questions at the end as well. Okay, I need to do a new share. Okay, can you see a slide deck which says compositionality in tasks?
Yes, we can see it.
Yes.
Okay, great. Okay, so this is going to be, so I had some general philosophy, and now I'm going to give some concrete stuff too. But I think the philosophy is essential for understanding the concrete stuff. Okay, so again, keeping the big picture in mind, vision exists to enable action in the real world. So we agree about that. So there is an agent, it's got a series of observations, then it acts in the world. So let's say there's a policy. Okay, so that's what we want to do. And what do we do today for this? So today we have a setup which basically treats every task as independent, and then we run our RL algorithm, and we have done yeah. So an extreme version of this is the framing pixels to talks. You have images, which are pixels, and then talks, which you need for every joint of the robot. And we train a connection between them with tons and tons of examples. And I think this is the wrong way to go about things. Okay, I think that this way every task is a separate task, and we don't exploit the commonality among them. It doesn't deal with abstractions, and it's often going to overfit to the very, very narrow training setup where the agent was initially trained. So we should really learn from child development and do things in a much more compositional way, if you will. So, so a critique of these end-to-end training for particular tasks, and then just having zillions of those. So these models don't generalize well to new domains, right? Because they're overfitted to that data. Tasks are treated completely independently. And then a new model needs to be trained for every new setting and task. And this is not a scalable solution. I mean, it's very inconsistent with biology for sure. But my point is that it purely in engineering terms, this is not such a great thing to do. Okay, so what should we do? Well, we should actually take vision seriously. Okay, what do we mean by that? So that means that we should create intermediate representations from vision, which are helpful to the larger system. And here a more philosophical statement. So the abstraction should be robust across many conditions and support a variety of downstream tasks. The model should be generic so that it doesn't need to be retrained for each new task. Okay, so this is why we can call this compositionality in tasks. And if you think about what neuroscience tells us about the brain, there are visual areas starting from the retina, various stages of computation, and those produce representations. And then there are other areas which are motor cortex and so on, which deal with generating signals for how the arm can move and so on. And these are connected, but we do have distinct visual areas, and they produce general representations. And those are useful if I'm just looking at an image or a video by itself without any action. So that's the kind of story we want to have. Okay, so how do we do this? So what we want to do is we need to look at the space of tasks now. Okay, so we have previously studied the space of object categories, right? So that's what taxonomies are. WordNet is a canonical example of a taxonomy. So there's a taxonomy of categories. So dogs, so there are different breeds of dogs, then there are dogs, then dogs are mammals, mammals are animals, etc., etc. We have exploited this in the past. That's one kind of hierarchy. Another kind of hierarchy is partonomy. So partonomy is that if you look at my body, in my whole body, there's a head. In the head, there are the eyes. In the eyes, there's a part, etc., etc. We can think about this partonomy for actions and events as well. But I'm going to talk about a different relationship. This is more in the action space. What's a relationship among different kinds of actions? And because we want to find commonalities and exploit them. So this is a series of papers that I'll talk about, and this is work with a number of people. The lead authors are Amir Zamir, who was a postdoc who worked with both at Stanford and Berkeley with Leo Gibas, Silvio, and myself, and Sasha Sachs, who was a student at Stanford and now he's at Berkeley, and various others, but I'm just mentioning these two for sure. Okay, so taskonomy. So the word taskonomy is itself taken up from this taxonomy and task, right? So this is a paper presented at CVPR 18. So what is the idea here? So the idea here is that we can take images and then we can do various tasks on this. So task means there's an image which is input xi, and then there's output yi, and the output yi could be what's the surface normal at every pixel. Okay, or what are the 2D edges, or what is the room layout, or whatever. So we can think of some of these tasks as geometric tasks, some of these are semantic tasks, etc., etc. And canonically in computer vision, what do? We have label data, we can train, and we are good. So we train each of them separately. But what we wanted to do was to say, what's the relationship among these tasks? Some of these tasks might be very similar to each other, right? For example, consider the task of estimating the depth and estimating the surface normal. If you know the depth, then you can differentiate and you get the surface normals. So these tasks are clearly related, and a system which can compute depth, it should be easy to have another layer on top which can compute the surface normals. So here we can analytically figure out what's going on. But what about all these other tasks, right? We don't have a natural analytical way to figure out how in painting helps you with respect to surface normals. So we can take a very empirical approach, and the empirical approach, the idea is you train a system for one task, and then how easily can you fine tune the output of this at the highest layers to accomplish another task. So that becomes a measure. So it's like so there's this concept of a readout function from a layer, which says that that we just have a linear function which reads out from a certain layer, a certain representation. And if that representation makes a lot of good information explicit, then that linear readout function should be sufficient. So if you start from an image, and then we want to have a function which detects dogs, right? From the pixels, you can't do it with a linear function, right? But from a sufficiently high level layer of a neural network, you can. So because the various stages of processing have made useful information more explicit. So that's the basic idea. So if two tasks are related, it should be the case that you could take the output of one, or the penultimate layer of one, and with just a little bit of work, you could get the output for the other. And then we have to do the work. We can take all these tasks and then see, train for one, then use it for the next other one, etc., etc. And that's I mean, there's a lot more detail than that, but this gives you the flavor of what this line of work is. And this has been built on by other researchers with ideas on how to consider the structure between tasks. Okay, let's move on. We'll take another idea related to the space of tasks, which is actually once we have the space of tasks, we can help them train each other. So suppose we were training a module which goes from X to Y. So that's your generic learning setup. And now we are training for two tasks, X to Y1, X to Y2. But perhaps the fact that you've trained these two modules gives you some additional constraints, because the outputs of Y1 and Y2 need to be consistent in some form. And this is a paper which will be presented at this CVPR. So let's take the idea. Again, I'm going to reuse the depth and normals example. So we have recovered a representation on depth, and we have recovered a representation of normals. And we could do this independently because we have training sets, right? So we have Xi, and then one Y could be the depth, and then one Y could be normals. We train them separately, independently. But the outputs we know that they should be consistent. So that gives us some additional information which might make the performance on each of the individual tasks better. But here we can analytically construct a story, but in general, we can't. So we have to again take an empirical approach. And the big idea is something like this, that we can get to some, so we start from some X, and then these YIs correspond to different outputs. So I can start from X, we can go to Y1, then to something else, then to Y2, or we can, so that's the blue path, or I can go through the green path, and they should give rise to the same Y2. So the Y2 representation should be the same, and we can compare that in some way. So that's the basic spirit. It should be reminiscent of ideas like cycle consistency and so on. But actually the core aspects here go back a lot. I mean, you can think of this as connected to, in physics, to the concept of a conservative field. You have the same difference in potential, whatever be the path that you travel on. So I can give you another way to think about it, which maybe is helpful. Actually, let me stick with the old slide. So I'm trying to build a system from English to French translation. Okay. Now, what I have, and let's say I already have an English to German translator and a German and a French to German translator. So I can translate from English to German and I can translate from French to German. So this gives me a way to improve my English to French translation. How? Because I can take my English to French translation and I can go from the French to German and I can go from my original English to German. And these two outputs should be the same or similar, right? So that imposes an additional constraint which can work back and make my English to French translation better. And ideas like this have in fact been tried in natural language with concepts like back translation and so on. So it's also related to that concept. And then we can go into details of how well does it work. And so here are some results where either you can train all these systems independently or you can enforce this cross-task consistency. And you can see that, and it's being done on a frame-by-frame basis, and you can see that the output is much more flickering at the top row than it is in the bottom row. And just by virtue of imposing this cross-task consistency, and the numbers get better too. It's less variable, the numbers get better, and it's more robust. So here are some so examples of, okay, so one was just more accurate, but very nicely it also generalizes. So here's this bedroom, this is of course this Van Gogh painting, and there's a significant domain shift here. But when you train systems in this cross-task consistent way, they generalize better to out of domain. The error, the difference between getting to a certain output from two different paths, that the error, the difference between those two outputs becomes an uncertainty signal, which again is of value. So, anyway, check out the paper at the main conference. Right, okay, now let me get to vision and action. And this is going to be about how do we, let's say, learning to navigate using mid-level visual priors. And this is work which was presented at Coral 19. So, right, so we are trying to do robotics. We have some world, agent, visual observation policy. And we can just run your favorite RL, PPO, whatever. The approaches, the algorithms are very, very sample hungry, and then they're brittle. They don't transfer easily from one domain to the other. So the vision part, we are essentially acting as if vision people can't do anything useful. No intermediate results are valuable. Okay, you're doing it all ab initio for every task. So instead, what we want to do is something like this. Sorry. So what we want to do is we start the agent, the vision system gets plugged into a mid-level system. So it can be those tasks which saw, the tasks which produce, say, depth estimates, surface normal estimates, corners, what have you. And now the policy training has to be done on top of those representations. And so we can train in pixel space, but no, we instead train in this representation space. So that's this phi p. And this phi you can think of as a vision system, which can go from pixels to depth, or pixels to normals, or pixels to corners or key points or whatever. And then we train the policy on top of that. And the idea is that in this space, this has been abstracted, and this will help us. So when we train, when we need to train for new tasks, you just have to train a different policy, but we don't need to train that representation again. That's going to work for multiple tasks. So that's compositionality, right? That first stage, the vision system is being reused in multiple settings. And again, you can look up the details in the paper, and the points that we want to make are the following. And then okay, I'm going to skip this. One is that you get better performance. And okay, so there are all the numbers compared. There's a second benefit, which is generalization from one domain to the other, or in this case, longer episodes. And the third benefit is accelerating learning, because RL takes lots of samples, and turns out you get to a high performance much more quickly. Okay, because the lower layers don't need to be trained. They're already pretty good. And the general presumption is having basically the early stages of filtering are going to be useful for multiple tasks. It turns out that it also makes the training much easier. So you don't have to do so much training, architecture search, ensembling, etc., etc. So this will make your life as a graduate student easier too. And then it can generalize a bit to the real world as well. So I'll end here, but this is meant to convey to you how an example of compositionality, which is to build vision systems for various tasks, recognize the relationships among them, and then build on them for doing motor action tasks like exploration, getting to a goal, so on and so forth. Thank you very much. With that, I'm happy to stop and take questions if we have the time.
Great, thank you so much. Yes, we do have a lot of questions, actually. So let me get started with some of our own, and then we'll move on to some of the audience questions as well. I wanted to specifically ask you about how you define mental models. In some sense, I imagine that neural networks that we're training are learning a variation of a mental model of whatever task they're being trained on. So for example, you could argue that mask RCNN, for example, creates a mental model of an object. However, it's probably not declarative or explicit. So what I want to know is, are you advocating for the development of some formal representation of a mental model, or a mental model that is more task agnostic?
Okay, yeah, what I mean by mental model here are models of how the world behaves. Okay, so think these are dynamic models that I'm talking about. So I'm talking about, for example, a models like Newtonian physics. So if I take an object and I drop it, it's going to fall, right? If I release, okay, or if it's liquid, it's going to behave one way. If it's a solid object, it'll behave one way. If it's marble, it will behave differently from rubber, etc., etc. So control theory people in robotics, they have models of dynamics, right? And then they insert them, and then they do their, they design their control loop based on those analytic models. So that's one example of a model. Another example of a model is what psychologists call schemas. Okay, so I'm at a restaurant, and then a waiter comes at some point and gives me a menu card. Okay, I think any third person would, what we expect is at some point somebody else will come and take my order. That's a model of a situation. So it's a dynamic model, right, of a situation, but it's much more abstracted, bit more complex. It's not just very straightforward the way Newtonian mechanics models are, and so on. So that's what I mean primarily by models. And these models can be used for planning. These can be used for prediction. I mean, prediction is one way to measure them, but prediction by itself is not of interest to me or to anybody. I think prediction has value mainly because it enables us to choose better actions.
I see. So you are advocating for a more explicit model that actually reasons about how the world will be changing.
Correct.
Okay.
Yeah.
Okay. A second question again about some of these high-level directions that you set up. I was wondering if you could talk a little bit about how you define being social, and again, what form of social interaction do you believe to be most important? And let me sort of preface this question by grounding it in Vygotsky's ideas around social constructivism, where he mentions that we either learn by observing experts or we learn by asking questions. And the idea of observing experts is very similar to what you talked about in terms of imitation learning. So I was wondering, which of the two directions do you have any intuition around being more important? Should we be focused more on observing and learning from experts, or building systems that can interact and learn by asking questions?
Both. Okay, so I'm glad you mentioned Vygotsky. I'm a fan of Vygotsky, this whole zone of proximal development and so forth. No, I think these are very good ideas, and I think we need to explore them all. So I think the setting which robotics people have used has been a very, very narrow framing of the problem, which is more like you just copy the sequence of motor actions and then you replay them. That's very, very trivial. I don't mean that. I just mean these much more richer notions that you talked about. So children learn by just observing, but the children also ask explicit questions. And then, of course, parents facilitate learning. So all of this is going on. So for me, learning, I mean, all of these are important, and we've done so little that we should just do everything.
So going off of that comment then, Vygotsky got a lot of his inspiration from Piaget, who you already mentioned. And, you mentioned that, you mentioned constructivism, and the way I sort of interpret it is that it encapsulates both lifelong learning, active learning, as well as curriculum learning. And you were talking about how we shouldn't be focused on just one of those because it's narrowing down the scope of the problem. So to move towards this vision of constructivism, are you advocating for research that attempts to combine these individual formalisms and tackle them all as one larger problem?
Yes, in a certain sense, yes, because I want us to get out of taking those individual sub-formalisms super seriously and just chasing up after them, and be willing to combine things at a bigger level. And then the question is, how will we do that, right? So what's a metric, right? So I think always in my mind, we have to just pick richer, juicier problems. So when we pick, so there are people who love technique, and then the people who love problems. I'm very much I love problems more than I love techniques. I'm willing to throw away one technique for another if it helps me with respect to richer problems. So I think as we are, as a community, if we tackle richer, juicier problems, we will see the need for slightly richer formalisms in terms of, whereas if we define the problem very narrowly, so I'll pick on this continual learning again. If the whole setup is, okay, catastrophic forgetting, we don't want that. Now we're going to divide up ImageNet into chunks, and then we will train on some, and then we'll see how good our performance is on the first chunk after we've trained it on the 50th chunk. It's a mathematically quite precise. You can get numbers, you can get your papers published in Europe, but like I don't find that so exciting.
Okay, let me ask you some of the audience questions. And if the audience wants to directly ask a question, feel free to raise your hand and I'll unmute you. So until you do that, I am going to pull out some questions that people have already posted. Kaidi says, thanks for the great talk. I was wondering, how does the cross-consistency work handle multimodality, since, as you put it, the field of tasks is not necessarily conservative? Also, does this require massive paired data across tasks to work? And what real work tasks you envision this can be applied to?
Okay, I think when you have a nitty-gritty question, I suggest you go listen to Sasha's talk at CVPR. So I'm going to stay at the big picture level. So
great.
I'll pass.
Okay, in that case, let me ask you some of the big picture ones. Here's another one from an anonymous attendee. You'd like to use mid-level features, but then you give up this end-to-end learnability. Do you think it's beneficial to give up end-to-end learnability?
That's a good question. So the question is that, do you, so you are learning end-to-end. I mean, but what you're trying to do is to not learn every part, right? So there's a tension here between modularity and end-to-end learnability, and modularity and compositionality go together. And the question is, will you land up paying a price for this, right? So let me give you an example from the Industrial Revolution, the early part of the 18th century, 19th century. So once you start to make parts, let's say you're trying to assemble some object and it has parts. So you can, if there is one part which is slightly big and you are assembling this whole thing as a craftsman, you can make the part into which it fits aligned to this part. and it all works together, right? So that's end-to-end training. For that one object you put together, you got all the parts to be lined up. Now, once you can make parts which are replaceable, okay, they're all identical, then life becomes easier because different people can reuse the parts as opposed to just doing the work for this one specific object. So it leads to a great deal of efficiency. Now, of course, nowadays, I mean, since this crafts is sort of popular for its own sake. The thing which I want to mention is the risk that you have, which is that are we losing performance? And I happen to have a slide on this theme, which is that in the straightforward way, you might think that you will lose performance because the fixed features will get you up to a certain asymptote. Whereas if you can do fine tuning, then you can go all the way, right? And you can get the highest performance. And in the naive way, where you have fixed feature detector, this is actually true. That you learn more quickly with fixed features, but at some level you asymptote, which may be at a lower level than if you allowed fine tuning all the way. So we have a trick for this called side tuning. And the idea is that you do a little bit of extra stuff which you train end to end, but the main pathway remains fixed. And again, there's some technical details, but that's a way you don't sacrifice performance, even though you're giving up. You're trying to get the best of both worlds by having most of the work be done by fixed modules which are recycled, and then some specific work which captures the end-to-end tuning.
Okay. Here's another question from the audience. Can we say that children get many examples because they observe any object in multiple frames? Is it fair to say that any continuous observation provides the child with heavy augmentation, like different poses and illumination?
Yes. So what, again, I recommend Linda Smith's talk yesterday in the embodied workshop. The clever insight is that children get a few objects with which they interact a lot. So the question is how you want to count the number of examples is up to you. But basically, there is this one object. Okay, so here is, say, my watch, and now I'm playing with it. So I see it from 1 million different possible views. And I really, really get to understand the three-dimensionality of it, all the different views under different lighting, with my hand covering up part of it, etc., etc. And so this very in-depth knowledge of a few objects seems to be very helpful, as opposed to superficial knowledge of lots of things. So it's like when you are preparing for an exam, one way of doing it is that you solve 100 problems quickly, or you take 5 problems which you try to really understand well, right? And when I'm recalling my time as an undergrad, I was the type of person who wanted to take 5 problems and understand them really well. And that's what children do.
Great. I think there was a follow-up question to a comment you made in the previous answer. It's from another audience member. The question is, if we train a model through step-by-step and not end-to-end, it might suffer from problems of dependence on previous probability components. Can you explain more about this problem? Do you think there's I guess this is a question about transfer and where learning components from different tasks might lead to different kinds of biases that might affect some other downstream tasks. I think that's what the question is trying to ask.
Yeah, no. In principle, that's a valid concern. I think that has to be addressed experimentally. But my generic answer is going to be back to side tuning, which you see in the slide right now in front of you, which is that we do a little adaptation which is specific to the task. So I have no problem with fine tuning, but there should just be a little bit of it and specifically for that task. And mostly it should work out of the box. So let me give an example. So learning tennis, right? Suppose we were to use RL for learning tennis. It would take you zillions of trials before the racket got anywhere near a ball. Okay. However, when I go to the tennis court and I have never played tennis before, I can do some things almost right away. I can take the racket, hit the ball, get it to the other side, right? Why? Because I know something about basic physics and rackets, collision, etc., etc. Somebody can instruct me maybe about what's a good service shot, etc., etc. So I can, in 5 minutes, I can start to play tennis, right? But it may take me a lifetime to get really good, or I may never get, I may just asymptote at a fairly low level compared to someone like Nadal, and that's fine. So that's what I want. I want that there is a stage of fine tuning, which you will do for a few things, few tasks which are really important for you. But most of the time we need something which works reasonably well almost right away, right? We don't need to become like the world's best tire of shoelaces, but I need to be pretty good, and I need to be pretty good quickly, right? So there are 100 or 1,000 different tasks that I need to be able to do quickly with very little specific training. We don't have to become the most efficient at everything. A home robot, why don't we have home robots? We actually have very good assembly robots because they are specialized for one task and they can be really optimal at it far better than humans. Humans can be second best at zillions of tasks. And currently our robots can be first best at one task. I think we need to move to that direction of being second best at lots of tasks.
Okay, here's another audience question. Hi, very interesting talk, Jitendra. I was wondering what's your views on adding extra capacity to an incremental learner and how that relates to learning in children, which start with a fixed capacity in some sense.
Yeah, so I mean, the example in front of us is one where we are adding a little extra capacity. Whereas, yes, in the case of children, there's some theories which say that only connections are pruned and not added. And yeah, I don't have anything very insightful to say there. I mean, I want to say that generally our approach in AI should be, we should be inspired by biology, but we don't need to, we can do stuff which we are allowed to do, but biology is not allowed to do, right? And we should not exclude that.
Okay, let me ask you a question based on something you said earlier about setting up the right sort of problems. And this is going back to our original question about mental models. One type of mental model that you hinted towards with knowing that a waiter would come to the table if you're at a restaurant. In that specific scenario, you're modeling other people's behaviors. And I think that's a very interesting line of work related to theory of mind and mental modeling. And one way to sort of set up that problem is to think about it in terms of some sort of inverse reinforcement learning, where you're trying to implicitly understand the latent sort of motivations and goals of others and use that to sort of define how they're going to behave. Do you agree with this sort of framing of the problem? Or is there something that's missing from this framing?
I mean, I do believe that we need to have models like theory of mind, right? Where we understand other agents in terms of their goals and so on. So I do accept I mean, for sure, we need something like this. And then inverse reinforcement learning is one particular mathematization or formalization of this capability. And I don't want to necessarily hang my hat on that. I want to hang my hat on the problem per se, which is that, yes, we are even 2-year-olds, 1.5-year-olds can infer other agents' goals. There are these great demos from Tomasello, which you can find on YouTube, which show that.
Great. I think we're at noon now, so we're at the end of this session. If there's a last audience question that you want to ask live, you can raise your hand. Otherwise, we're ready to end. So I'm going to give it a couple of more seconds in case someone wants to raise a hand. Okay, I think that's it then. Thank you so much for this session, and we'll see you later in the afternoon for our panel session.
Thank you very much.